But let's go. So let me give you a brief overview of what we're going to do today. Same schedule, of course, as always. My first lecture this morning, I'm going to talk about hack standard errors. And I learned a lot about them while preparing this, so it's kind of fun and at least fresh to me. And then I'll talk about, so that'll be the first set of lectures, and then I'll talk about some issues in forecasting. And there's been a lot of work on forecasting and tools, some tools for forecasting, but really tools for assessing forecasts that I will concentrate on in my part of the talk. Jim will talk, so that'll be that lecture, and then Jim will come this afternoon and talk about models in which you have, not only a long time series, but you have lots of variables that you're studying. And he'll talk about some advances in forecasting that have been made in the context of those models using the rich cross-sectional information to help you forecast a particular series. And he'll also talk about, how these kinds of data sets and this sort of rich cross-sectional information might be useful for other things, structural vector autoregressions, DSGE models, and some of the things he talked about yesterday afternoon. Okay, so let's just get going. So this is the topic. I'm going to do. So what I'll do, I'll just remind you. We've sort of done this already, but most of you have pushed, if you will, the New West button at some point in your life. But I'll remind everyone why you push the New West button, and that's in one, or why you use hack standard errors. And then I'll talk about actually why you push the New West button and not some other button. And why that might be a good thing or a bad thing. So that's parametric and non-parametric estimators. The New West thing, of course, is in this non-parametric estimator group, and I'll talk about some parametric estimators as well that are quite natural. And then I'll talk about comparing these different estimators and what are the important choices that have to be made, which estimator to use, and then within an estimator, some details about lag length choice and stuff like that. And I'm going to try and highlight here, what I think, at least in my reading of the literature, has suggested are the important choices and what are the choices that aren't important or that are minor. And then I'll move to some really exciting work that's been done over the last several years on thinking about this problem in a different way and using inconsistent estimators for this sort of thing. And I'll probably do this. I'm sure I will do this sort of historically in kind of a sequential way. But we're at the end of the day, we're kind of used to thinking about using inconsistent estimators. In some sense, when you took, your old Stat 1 course, right? You had, 12 observations from a normal, and you were estimating a mean and constructing a confidence interval or a t-test, right? And you used the t-distribution, and you worried about this thing in the denominator being, s squared and not sigma squared. Then you adjusted the degrees of freedom, right? So we've all done that, and this is just that, right? This is just that where you have, in some sense, lots of data. You've got a long time series, but you don't have data information where you need the information. So you really sort of, at the end of the day, in some sense, have 12 observations. So you kind of go back, if you will, to using t-statistics and t-distribution. So that's the way I'm going to think about this. Okay, so that's where we're going to go. Okay, so this is just a reminder, why do we do this stuff? What's it all about? So, linear regression, y equals x beta plus e. I called it e here. I don't know why I called it e, but I did. And So, beta hat is blah, 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 right? And, you work out the, you can rewrite, beta hat minus beta as, so this is, of course, the error that one makes, the sampling error in beta hat. And the sampling error really has, 2 bits to it. It's got this sort of scale factor, if you will, the normalized x prime x inverse, right? And then it's got this, this part, x prime e, this sort of average of, the x's and the e's. We know, of course, for consistency, as we talked about, again, Econometrics 101, one needs regressors and error terms to be uncorrelated with one another for this term in some sense to have an expected value of 0 for this thing to be consistent. But this is going to have some sampling variability. It's an average, so, the sampling variability is going to be the sampling variability of the average. So when one, works out the distribution of this, right, what do you find? Well, this is kind of an average, so, this estimator is going to be, normally distributed. It's going to be normally distributed with a variance, which is this scale times the variance of this bit, which I've called A here, I guess. Right? And so what do we want to do to work out the variance of this thing, which we need to do inference, right? What do we have to do? Well, we have to characterize the variance of A. That's this thing called omega. So we'll do that. Here, and we'll do that in the next slide. And then we have to think about estimating this variance, right? So we'll characterize the variance. That's simple, and then we'll estimate it. That's hard. Okay. So this is, if you will, this is sigma squared, right? And this is sigma hat squared, and we have to figure out what a good sigma hat squared is. Okay. So that's it. So this is the hack problem. What estimator should I use? Okay. So let's. Here's some notation I'm going to use. This is what we care about, right? We care about, this is the object that we want to estimate. What's the variance of this guy, right? And I might as well just call this guy, this is x times e, but rather than writing out x times e over and over again, right? Why don't I save pixels and just call it w? So w is going to be x times e, right? So what we care about is what the variance is of 1 over square root of t times the sum of these w's. Now, as a practical matter, of course, when we construct estimators, right, for, regression problems, we don't know what the e's are, right? The only way you could know what the e's are is to know what the beta was. So you could subtract and get e, and if you knew what the beta was, you wouldn't be going through all of this stuff to begin with. So, we have to replace e with, the residual or something e hat, okay? Except for one little bit at the end, this replacing e with e hat is not important for the things I'm going to talk about for most of this, okay? So I'm just going to, notationally run around with w, right? And an estimator would have a w hat in it. Those are going to have the same properties with one exception that I'll sort of highlight at the end, right? And you could imagine there are sort of technical assumptions you would want to make about moments, right? So that e and e hat can be treated the same way in the kinds of calculations I'm going to do. Okay? Okay, so I'm going to construct an estimator. My estimator is really going to be a function of these w hats, right? But I'm going to write it or characterize it for most of the things as just a function of the w's. Okay? So omega hat's just going to depend on the w's. Okay, so omega hat is an estimator of omega, right? What is omega? Let's just write it out and see what the heck this thing is, right? We did this the first day, but this is just a review, I guess. So what's omega? Omega is the variance of this, right? So it's the variance of a constant times a sum. So that's the constant squared, 1 over t, times the variance of the sum, right? And the variance of a sum is the sum of the variances plus all of the covariances, right? So, let's think about these w's as being covariant stationary, So when I talk about, covariances, the covariance between W1 and W2 is the same as the covariance between W2 and W3, same as the covariance between W50 and W51, right? So I can then rewrite this as I've got the sum of the variances. All these guys have the same variances, so that's gamma naught, and there are T of them. And then the cross products of the adjacent terms, right? They're going to be T minus 1 of those, W1 and W2, and then those kinds of things, and then T minus 1 of the W2, W1, right? I got, if you will, 2 times the covariance. And I've written it like this. I don't know why, but instead of just 2, it's because I've written this out, so these guys could be vectors, in which case one would be the transpose of another. I should say that actually when I do these calculations, I'm going to assume W is a scalar, so I don't have to put transposes on things, okay, because I would forget half the time, and that would just make this more confusing. Okay, so boom, so you do this for all of these guys, right? And then notice, you've got T and T and T and dot, 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 if you will, T, and I've got a 1 over T out in front, right? So, part of this simplifies really easy. It's just all of the little T bits here cancel with this T, and I get this, right? The sum as J goes from T plus 1 to T minus 1 times these gamma J's, right? And then I've got, there was a minus 1 there, right? And there's a minus 2 there, right? Dot, 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 there's a minus T minus 1 there, I guess. So I got to keep track of that component. Okay. Now, the key thing is if you look at this, right? If you look at this, this bit doesn't have a T in front of it, right? So as T gets big, this just is going to behave like, it's going to behave like the spectrum at frequency 0. It's going to be this one, right? And this thing has a T in front of it. And as long as these guys don't go wacky, right, as long as the memory dies off sufficiently fast that the covariances die out, right? You think about an AR model, they're dying out, geometrically or exponentially, right? This term without the 1 over T in front of it's going to be finite, right, or bounded. I divide by T, it's going to go away, right? So this is the important component, and this is just, this is just little stuff that we're going to ignore. Okay? So we can think about what we want to, we can think about omega, if you will, the limit of this as T gets big, right? It's just the sum of all the autocovariances. And, from the first day, right, remember the spectrum, we had this formula, right? And as I mentioned, stick in omega is equal to 0, so the lowest frequency component, right? So I get e to the 0, which is 1, right? I get really the same formula scaled by 2 pi, right? So this is the long-run variance, okay? And you can, of course, now immediately see the estimation problem, right? Whenever you're estimating something that requires you to have 2 times infinite amounts of data, or you need to estimate 2 times infinite number of things, right? And you've got 150 observations, you can't, right? Or it's very easy to construct examples in which any estimator you write down is going to be wrong, like way wrong, like as wrong as you can want it to be, right? So cooking up, pointing out that, gee, this is really hard to estimate in certain circumstances is like, here, we're done, right? Okay, and, so that's that. Okay, so let's keep moving here, okay? So let's just go, so the first thing I'm going to do is, right, we talked a little bit about, what the spectrum was on day 1, right, and I guess I quickly went through what the spectrum is for an ARMA process, right? So for an ARMA process, I wrote a little formula for what the spectrum is, right? So the first kind of estimator that you might think about is, gee, if W follows an ARMA process, I can calculate what its spectrum is. I can write out the spectrum in terms of the AR and MA coefficients, right? if I can do that, well, just take that thing, stick in 0, right? And then I'm going to get the spectrum at frequency 0 for an ARMA process. It's just a function of sigma epsilon and the thetas and the phis. I can go out and estimate sigma epsilon and the thetas and the phis, stick those guys into the formula, and I've got an estimator. Okay? So that's called a parametric estimator. Parametric because you estimated some parameters of the ARMA model. Right? If you just looked at an AR model, it would be called an autoregressive spectral estimator. This is just jargon, right? And if these were vectors and you looked at a vector autoregression, that would be called a VAR spectral estimator, I guess. Here, associated with this problem, that would be called a VAR hack estimator, or hack VAR estimator, or something like that, right? So hack VAR together is just that calculation. Okay? So I guess that's what this slide says. So this slide says, suppose W is ARMA, and later we'll talk about suppose the W process could be approximated well by an ARMA process, right? So, the ARMA process has this form. Here's the little formula that I wrote down for the spectrum in day 1. It seems like about a month ago. 8.5 lectures ago. Geez, about like 8.5 weeks worth of teaching ago. And for you guys, it's like, anyway, never mind. Right? At least Jim and I get to walk around and talk. You guys have to sit there and go, stay awake, man. Stay focused. Okay. So, right, what are we going to do now? Well, we care about this guy at frequency 0, so stick in omega is equal to 0, e to the 0 is 1, right? So that says take these moving average polynomials and evaluate them as at 1. So whenever you saw an L, right, whenever you see an L in this formula, you stick in 1, right? And boom, you get the formula for omega. It's going to be sigma epsilon times 1 minus the sum of the moving average coefficients, quantity squared, divided by 1 minus the sum of the AR coefficients, and I guess that traditionally would be called P, right? So that the AR order is different than the moving average order. And the estimator just says stick in hats on things, put hats on things. So go out and estimate an ARMA model and stick in hats, right? Now, if these estimates are consistent, right? Continuous mapping theorem, or Slutsky's theorem, I guess this guy's going to be consistent, right? So boom, we're kind of done. We have a consistent estimator. VAR, so someone just said I had to mention VAR hack. So I put the slide in which says VAR hack, and it's just the same thing. This is now a vector. These guys are now matrices, and and then there's a transpose right there, right? So this is 1 minus the sum of the AR coefficients squared inverse times 1 minus the sum of the AR coefficients inverse, right? And then that's the sigma epsilon, right? So same thing, right? Same thing. Okay, so those are parametric estimators. So parametric estimators generally, we're going to think about parametric estimators are generally estimators that are constructed from parametric models. The natural parametric models to use here are these linear, finite order, AR, or moving average, or some combination of them. Okay? And we're going to see that these guys, in lots of circumstances, seem to have some very nice properties. Okay? Non-parametric estimators. Well, that's kind of the guy you want to estimate, right? And so, the sort of natural thing to do, I guess, is to say, well, heck, that's just the jth autocovariance. I can just estimate that guy, right? So you just estimate the autocovariance, right? And so that's the jth of those. You take that guy, you stick it in there, right? And then you say, oh, heck, I can't go to minus infinity and plus infinity, but I can go some of the way, right? So you stick them in and you go some of the way, right? So you truncate this thing, right? And you stick in these estimators, okay? And maybe, we'll come back to this, right? Maybe you're going to say, I'm going to put some weights on those for reasons that'll be clear in just a few minutes. Okay? And, these weights are like the Newey West weights that, you know. Okay? So these are non-parametric estimators. Let's talk about a couple of issues. Let's talk about some issues with these estimators. Okay, one thing is, this is a variance, right? And variances are non-negative, and it's nice if you have estimated variances being non-negative, right? So you don't get, so you don't take the square root of a negative number because that's not good, right? So it's kind of nice if you can constrain the estimator, which is the function of the data, constrain that function to be non-negative, right? And we do that, of course, when we, Stat 101, right, our estimator of sigma squared is s squared, which is, right, a function of some, a sum of squares, right? So that's never going to be negative, right? So it's going to be kind of useful if we can write our omega hat as like a sum of squares, right? Because then we have it constrained, right? And we'll see that some of the natural estimators can't be written that way, right? And so there's a problem, right? And then I guess we need something like, how much memory are we going to allow in our estimator? In the AR models or the moving average models, right, the way you think about memory, how much serial correlation you're allowing is how many lags you're sticking in. Is it an AR4, an AR12? Are you throwing in an MA term, et cetera, right? So we'll want to think about lag link selection in those models. And in, the non-parametric estimator, it's kind of clear how big is M going to be. Okay, where are you going to do this truncation? And then I guess also related, right, in the non-parametric estimator, right, what are these K weights? What are those all about? And what kind of choices do you want to make there? So that's the kernel choice, right? So we'll want to talk about that. And then we'll talk about some robustness at the end to some things. Okay, so that's where we're going. Okay, so the first one is this estimator, right? The true omega is positive semi-definite. It's a covariance matrix, right? So is the estimator positive semi-definite, right? So here's a scalar. It's a scalar case, so that just means is it non-negative, right? And if you think about our parametric estimator, it's a squared thing times a squared thing divided by a squared thing, right? So this is as nice as can be, right? So it's not an issue here, right? Of course, this thing is going to be positive semi-definite. Okay. This estimator isn't, right? And I guess the easiest way to think about this, or an easy way to think about this, is just to think about the MA1 case. So suppose your W's followed an MA1, right? They really did follow an MA1, right? And you knew that, okay? So what would that mean? Well, if you constructed, what's omega, right? Omega is just going to have, the variance and the first autocovariance in it, right? All the other guys are 0, right? And you know that, right? So then the natural estimator to use is just to estimate these 3 guys, right? And just stick them in, right? And that would be the natural thing to do, right? Now, the problem is, of course, right, thinking about a moving average model, right, with an MA1 model, right, it so happens, of course, that, the AR1 coefficient, right, is less than or equal to the variance divided by 2, right? You can kind of work that out, okay? That's true, right? And that's going to be satisfied here. That guy's always going to be positive, right? So that's fine. But now, start adding some sampling error to these guys, right? You add some sampling error to these guys, and maybe this inequality is going to be violated, right? And if this inequality is violated, boom, suddenly that guy turns out to be negative, right, when that guy's positive, right? So you got this embarrassing situation. You computed a variance, and it's negative, and you can't compute a t-statistic. Maybe you could do, anyway, okay. So this is an important problem in this non-parametric estimation, right? And and it was solved, right, in this important and well-known paper by Newey and West in 1987. And they said, gee, if we choose these weights in just the right way, right, we can constrain this guy. This guy will be constrained to be non-negative, right? And they said, here are some weights, right? So this is called the Bartlett kernel. It turns out to be what guys doing spectral estimation had been using to make a spectrum's just a variance, right? To make estimated spectra non-negative, right? So they said, well, let's use the same thing here because after all, we're just estimating a spectrum, right? So two contributions to this paper. One is you can do this to make it positive, and like time series guys sort of knew that, or these guys looked this up in a book, right? But then showing, importantly, that this guy's still going to give you a consistent estimator, right, is a non-trivial calculation, right? And that is technically the sort of the hard part of this paper. Practically, the useful part of this paper is this guy delivers a consistent estimator in ways that I'll be clear in a second, and it constrains this guy to be positive semi-definite. Okay, so this was like 1987. Some of us were alive in 1987, and this was like big news, right? This was like, you probably remember this, right? So, yeah, okay, so this was really big news. You knew the guys, right? So I thought I would list some of the other things that happened in 1987. That were reported on, this is just so happens they're reported on the front page of the Wall Street Journal. So, the Dow broke 2,000. Texaco, remember Texaco? They're still around. But anyway, they filed for bankruptcy. Gary Hart was a sleaze. Gary Hart paid for being a sleaze. Some guy who is not on the Supreme Court is apparently a drug addict. Cal Ripken, consecutive innings is broke. Oh, there was Black Monday too. Okay, so that, okay. But of course, right, you remember, right, the most important thing reported on the front page of the Wall Street Journal was that Newey and West, right, had solved this problem, right? So if you look at the Wall Street Journal, July 21st, oh, this is 1986. Oh, drat! I completely messed up this joke. It's because the guys at the Wall Street Journal, right, they're looking for scoops, so they're not going to wait for Econometrics to come out, right? They're going to read the technical working paper, right? So there's discussion about, the NBER technical working paper. This technical working paper comes out, so it's in this guy's front page of the Wall Street Journal, 1986. Don, I got to fix that. And does anyone remember this article? I remembered this and spent actually a long time, a couple weeks ago, trying to find this particular article. It was this really terrible thing about, it was one of these columns over to the right, and it's this guy talking about like all the junk he gets, right? And he can never keep up on all his reading because he gets all this junky stuff, right? And he says, in particular, the NBER just sent me something called a simple positive semi-definite heteroskedasticity and autocorrelation consistent covariance matrix. What am I going to do with that? Right? So I remembered this and thinking, God, that's kind of nasty because, this actually, we're sort of joking, but, this was like a really important paper, right? And in the scheme of things, right, this, was more important than Gary Hart. Who cares? Okay. So anyway, I got to fix this slide before this. Okay, so again, just a reminder, right? Newey West are considering estimators of this form, right, with this kernel, this triangle kernel. Okay. So what I want to do now is spend a couple minutes talking about, it's not obvious if you look at this why this makes this positive, right? And setting k is equal to flat, like, doesn't, right? So it's kind of useful to do a calculation or to transform this so that you can see that this is just a sum of squares. And it's a sum of some kind of squares that are pretty nice. I mean, that are interesting squares, right? Squares that are going to be hanging around for a while. Squares of some objects that are natural ways to think about this long-run covariance matrix. Okay, so let's do that. Okay, so let's start. Right. So what are our what's our data? Our data are these W's. Okay. So we've got W1 through W capital T. Right. Those are our data. So let's put that all in as a big vector W. Right. And W, right, has mean 0 in some covariance matrix. Remember, this guy's covariance stationary. So the covariance matrix actually has a very special structure for this W. Come back to that in just a second, right? Well, we know, right, I can always, if I've got some W with some covariance sigma WW, if I take W, I multiply it times a T by T matrix H, I get U, right, and U is going to have some covariance matrix sigma UU, which is just, this, if I did it right, right? And, there are, some ways that one could think about choosing the H's, choosing the rows of H's, right, so that the resulting covariance matrix of U is diagonal, right? So you can diagonalize this covariance matrix. And we know there are lots of ways to do that, right? Okay. Well, what we're going to do here is choose an H so that D is diagonal, okay? And what's pretty nice about this problem is that this sigma WW matrix is special, right? It's got the diagonal elements are all the same because it's covariance stationary. The first off diagonal elements are all the same, right? And those are the transposes of the diagonal of the just below the diagonal, right? So this matrix has a lot of structure in it, right? And it turns out that the H that you can diagonalize this matrix with, right, is there's one H that works for like all W's with this structure, or at least approximately works with all W's with the structure, right? So that's that's going to be these Fourier coefficients. I'll show you them in just a second, right? The important thing about this, if you chose this particular H, right, is that these U's are really nice, right? The first of them, right? Remember, these U's are all, they have a diagonal covariance matrix. So these U's are all going to be uncorrelated with one another, right? If these were Gaussian, these U's would be independent of one another, okay? So what's the first one? The first one, well, they all have mean 0. The first one has mean 0, and what's its variance? Its variance turns out to be the spectrum at frequency 0. That's just what we want, right? Now, what about the second? Actually, the second and the third. These guys are going to be independent of one another, uncorrelated with one another, and everything else, right? And they're going to have a variance which is the spectrum, but evaluated not at 0, but at 2 pi over t times 1. Okay, now, if t is big, right, 1 times 2 pi over t is really small, right? So this number is going to be kind of close to 0, right? So the variance of these guys is going to be pretty much like what we want, right? And this guy is going to have U4 and U5. They're going to be uncorrelated with everything else, and they're going to have variance, well, 2 pi over t times 2. Again, if t's big, right, 4 pi over t is pretty close to 0, right? So these guys are going to be kind of useful, right? And then you're just going to kind of keep going. I've done this for an odd number of observations, so I can use integers here in a nice way, right? And boom, boom, boom. You get down here to the bottom, the last of these guys, right? The last of these guys, well, this is now s at t minus 1 divided by 2 times 2 pi. So this is like I don't know, S at pi or something as t gets big, right? So that's not close to 0 at all. So these guys aren't very important, right? But these guys are. Yeah. Well, because the way I've done this, so these are going to be, I'll show you in a second. Okay. I could have used the cosine transform or some other transform in which I wouldn't have done that. But so these I'll show you. Okay. And it'll be familiar. Okay. So now, so here's some algebra that I'm not going to show you. So this is the Nui West. This is this class of estimators. Right. Remember this guy, gamma hat is a function of the W's, right? It's these autocovariances, right? If you mess around and do some algebra, I'll show you a little of the algebra on the next page, right? A little of the algebra on the next page. Turns out you can write this like this. Okay, this is going to be the Periodogram Ordinance. Okay, so it's the modulus of this complex guy. So I want the sine part and the cosine part. So that's why I have two. So that's the sine guy, that's the cosine guy. Okay, so now you can do this. Okay, so now these guys are called Periodogram Ordinance. I'll show you some algebra in just a second, which sort of tells you what those guys are. Okay, but now it's kind of pretty easy to see, right, what constraints you need on these capital K's to make this guy positive. Well, these little k's are functions of the big K's in this H matrix, but that's fixed, right? So, I guess I need big K's that give rise to little k's that are positive or non-negative, right? If I have any of these little k's are negative, right, then I got a negative times a positive, and I can end up with a negative estimator. Right? So we could analyze these estimators by deriving the little k's from the big K's. These are Fourier transforms of these, right? So we could do that in an easy way, and we could just look. You propose some big K's, I Fourier transform, I find the little k's, and I look at them and I go, are any of them negative? If any of them are negative, I say, go back and try again. Okay, so that's what we're going to do. Okay, here's some algebra which just says what these U's are. What's nice about this, I'm not going to spend time on this, but what's nice about this is this turns out to give you formulas that look almost identical to the formulas that we talked about the first day, relating spectra to autocovariances to spectra, Kramer little increments z to the observed data, right? These C's are transformations of the observed data. So these are like Z's, if you will, in the Kramer representation, right? And my U's are just the modulus of those guys, right? And those can be written as the Fourier transform of the sample autocovariances. Okay, now, what's nice about this is, going back here, remember the spectrum, right? The spectrum is like the sum of all of the gammas times transformed by the cosines. The true spectrum is the sum, t goes from minus infinity to infinity, of true autocovariance times cosine, right? This puts in sample versions of those and truncates. So this is kind of like a natural estimator of the spectrum at frequency omega j. So let's go back here. Let's go back here. So this says, gee, one way to estimate the spectrum right there, these guys are both independent of one another. They have mean 0, right? So one way to estimate the spectrum right there is to square that. That has expected value that. Square that. That has expected value that. Average those two things. So that's a natural estimator of the spectrum. Now, of course, it wouldn't be a very good estimator because it would be an estimator based on 2 observations, right? So it wouldn't be consistent, right? But it would be unbiased, right? And if I wanted to construct an estimate of the spectrum at any other frequency, I could do the same kind of thing, right? I'd have an unbiased estimator at that particular point, but it would be based on 2 observations, right? So it would be highly variable. Okay? So this periodogram, the periodogram, which is this, right, is a nice unbiased estimator of the spectrum, a natural estimator, but it's not very good because it's highly variable because it's based on just 2 observations. Okay. So, what do I want to say now? Oh, okay, so now let's do this, right? Remember I told you the NBER thing, path breaking because it implied these guys are positive. Well, I guess what I should do is show you the little k's that come out of the NBER thing. Jargon. Oh, wait, I'm sorry. I've gotten ahead of myself. I've got to rewind. Okay, so forget what I just said. I'll say it again. What does this slide say? I don't know. I'm going to have to read it. Okay. You know what I wanted to do? I tried this yesterday. I wanted to see how far away I could get and still be able to change. See, I can do it there. I think you can do it from the back of the room, but the laser pointer quits. It kind of moves out. Okay, anyway, let me get back to work. This should be a 0 right here. That's a typo. That should be a 0 because that's the 0th guy. I think. No, that's right. By the way I define this, that's right. It's a thinko, I thought. So there's a 1. Okay, now remember what we had. Let's go back here, right? This guy squared, U1 squared, is an estimate of what I want, right? But it's based on only 1 observation, so it's not going to be very good. These guys, right, if I squared these guys and average them, it would be an estimate of this. This is not what I want, but it's kind of close to what I want, right? Because, if the spectrum is kind of smooth, the spectrum right around 0 is going to look like the spectrum at 0, right? So these guys squared are an estimate of almost what I want. These guys right here, U4 and U5, are also an estimate of not what I want, but of kind of sort of what I want. They're a little further from what I want, right, than this guy, right, which is a little further from the truth. Okay? So as I go down here, right, these guys become more and more biased, become less and less good. Okay. So, right, what do I want? I'm interested in estimating the spectrum frequency 0. So it better be the case that when I think about these different estimators, as t gets big, right, I need all of this weight to concentrate around, right, the spectrum at frequency 0, right, so that this bias goes away. Now there's some jargon here that it seems to, the jargon is, you see this written down in papers and computer manuals, and different words are used for the same thing, and it's kind of confusing sometimes. So I've just listed some of these. Kernels, sometimes kernels mean capital K, sometimes kernels mean little k. So when you see kernel, it depends on the context, what it means. Okay, so that's bad, unless you're really into the context. Okay? These K things are sometimes called lag weights, because they're weights on lagged autocovariances. That makes sense, right? So, for example, the RATS manual, right, calls these K weights, it says, the word that it used, you say L window equals NBER West, right? L window, lag window. So that's why the RATS then calls it L window, right, which is kind of natural, right? These little K weights are sometimes called spectral window, right? So that's a nice, this is like Priestler, this is one standard bit of jargon. So I like this lag window, spectral window. Kernels are confusing because it can mean either. Okay, but I'm going to use kernels too when I talk about these. Okay, so now here's this kernel, right? So this was this kernel which says, keep the first 3 or the first 5 autocovariances in your estimator and leave everything else out, right? And weight these all the same. So this was like our MA1 thing where we weighted things equally, right? And if you compute, I guess this was for m is equal to 12. You keep the first 12 and you weight them all the same, right? So those are your k weights, right? If big capital K weights, if you compute the little k weights from those, right, you can see, well, the key thing is they go below 0, right? So these periodogram ordinates that are down here are going to have negative weights associated with them. If they turn out to be big, squared things, right, you're going to get negative, you're going to have a negative estimate. Okay? Well, here's the Nui West thing, right, and lo and behold, right, the Nui West thing gives you positive little k weights, right, which is why it is so famous. Okay. Next. Okay, so now let's go. What's next? Okay. Implementing these estimators. To implement these estimators, well, we've had 2 kinds of estimators we've talked about. We've had parametric estimators. I'll call those AR estimators or VAR estimators because that's generally how they're done. I guess if you really thought something was an MA1, you should estimate an MA1 and use that, not an AR. But ARs are typically easy to use because they're trivial to estimate, right? And so you might want to use those, right? There are some choices, how big should lag length be, right? And there's some theory which says basically if it gets long enough at the right rate, everything is great. I mean, that is, you get a consistent estimator just like Nui West. So that's this famous paper by Burke. That really doesn't give you much guidance about how many lags you should stick in your autoregression. Probably something like AIC turns out to be not a bad idea. BIC probably, for reasons I'm going to talk about in a little bit, is probably a bad idea because it probably chooses too few lags. So the general rule that I guess that I want you to come away with this is if you're used to using an AR4 to do AR stuff, don't use an AR4 here. Use an AR6. Stick in a few more lags for reasons that'll be clear in a little bit. So put in a few more, okay? And I'll show you why, okay? Okay. There's a paper by Serena and Pierre about lag lengths in ADF tests. Some of you may know that. This is kind of a similar issue because part of what they're doing is estimating a spectrum at frequency 0 there. But there's also some bias that's going on in those kinds of situations, so it's slightly different. Okay, so what you have here is the sort of standard kind of, if you put in few lags like you do BIC, right, you've estimated fewer parameters, so you've got smaller variance, right, but the chance of omitted variable bias is higher. You've left stuff out, right, so you got a larger bias, right? Longer lag, smaller bias, larger variance, so you might want to think about a mean square error trade-off. I'll argue in a little bit that probably mean square error isn't the right way to think about this. Bias turns out to be more important than mean square error would suggest for some kinds of questions you might be interested. So practical advice, choose lags a little longer, and rationale. Anyway, I'll talk about it later. Okay, how should M be chosen? So I'm going to talk about 2 things. I'm going to talk about, in these non-parametric estimators, what kernel to use. Do you use Nui West? Do you use this truncated thing? Well, no. You don't use the truncated thing because you get negative numbers, right? So no one uses that. People use K weights that give them positive things, and there are a bunch of them, right? So which do you use? Do you use Bartlett? Do you use quadratic spectral? Do you use Parson? Do you use Tukey-Hanning or Tukey-Hamming or, those things, right? I'll talk a little bit about that. And how many lags do you stick in, right? How many lags do you stick in? Where do you truncate this thing? Okay. So let me talk about this, right? And let me just review a couple of results that are important, and again, that many of you have probably seen, right? Which is important paper by Don Andrews in 1991, in which he considers what kernel you should use and what M you should use, and another important paper by Whitney and Ken, in which they talk about, for the Bartlett kernel, what M should you use. And both of these papers talk about mean square error, right? So you want to get the most precise and a mean square error estimate of omega. Now, that might not be really what you want to do, right? Because at the end of the day, what are you going to use omega hat for? Well, maybe you're going to use it as, the denominator, or square root of it is the denominator in a t statistic, and you're going to construct confidence intervals or something, right? So what you care about, if you're using it for that, is when I stick it into the confidence interval formula, do I get confidence intervals with the right coverage, right? Not, is this a good estimator in a mean square error sense, right? If you're using this as an optimal weighting matrix in GMM, that's a different thing, right? Then that might be closer to, I want a good estimate of that weighting matrix, right? So that might be closer to a mean square error thing. So maybe maybe that's kind of the way to think about this, okay? But let's just keep going. So these guys are interested in, how do I choose M to minimize mean square error? Well, here's the formula for the estimator, right? We just talked about if you make M bigger, right? If you make M bigger, you're averaging more points, right? So just go back to this, right? If you average more of these guys, right, you reduce variance because you've averaged more independent guys, right? That's good, right? But if you've averaged a bunch of these guys, you've averaged a bunch of these guys that aren't particularly useful, are biased, right? So you get a big bias, right? So there's this bias-variance trade-off here, right? Now, the variance is straightforward. You average more guys, you get lower variance. The bias is a little bit subtle, right? Suppose this process was white noise. If it was white noise, the spectrum would be flat, right? All of these guys would have the same variance, and they'd all have the variance that you want, right? So in that case, there's no bias, right? You want to use all of these guys, you just want to minimize variance. So the bias is going to depend on how flat this thing is. How close are these guys to the thing that you want to estimate? So is the spectrum real flat at the origin, right? Or is it real curved? Okay? So that's what you need to know, right? To figure out what the lag length is, you want to know how curved the spectrum is, right? And to know that, I guess you need to know what its process is or something. So that's what these papers carefully work out. That's what these papers carefully work out. Here, let me just show you. Let me show you what happens as you change M in the Newey-West thing. Okay, so here's the Newey-West thing. It's the tent-shaped thing. The lag window is tent-shaped, right? Let's look at the spectral window. These are the little k's. Okay, and let's ask what happens as I increase M. Right? Here's M is equal to 5, right? And what am I doing here? Well, I want to estimate the spectrum at frequency 0. So I want to put lots of weight on the guys around frequency 0, right? But, I'm going to put some weight on these guys as well because I want to reduce variance, right? So this guy's going to work pretty well if the spectrum's pretty flat around here, right? Because then putting substantial weight on these guys out here isn't killing me in variance. Here's m is equal to 10. So make this, right, include more of these variances, autocovariances. Well, what happens now, is these k weights, right, get sort of pushed towards 0. So when is this going to make sense? Well, this is going to make sense. Well, I'm a little bit more worried about the spectrum at frequency 0. I don't think it's quite as flat as I thought it was here, right? It's got more curve to it. I'm more worried about bias, right? So I'm not going to put very much weight on these guys out here because they're not what I want, right? I'm really concerned about bias. Here's m is equal to 20. It's being squished more, right? Here's m is equal to 50. This is what t is equal to 250, right? Now here, we'll come back to this guy. We'll come back to this guy later on. This is an example of something where you're putting lots of weight on just a few u's close to 0. That makes a lot of sense, right, if you've got a lot of curvature there, right? And so you're just going to include a couple of the guys. This guy's going to have big variance, right? But it's going to be very robust, right? It's going to be very robust because it's not including these other frequencies, right, which may be badly biased, which may not be close to what it is you want to estimate. Okay? So key thing that I want you to remember here is as m gets big, right, these guys, you're putting more and more weight on just a fewer of these u's, of these periodogram ordinance. Okay? Okay, so here are the numbers for the mean square error minimizing values of m. They depend on how curved the spectrum is. So these calculations are done for a W process, which is an AR1, right? And as the AR coefficient goes up, the spectrum gets more steep, right around frequency 0, so it's more curved, so there's more bias, so you want to use a bigger M, right, and put more weight on those U's, right? So this is the formula that's worked out in the Andrews paper, and this is for the Bartlett kernel, so it's also worked out in the Newey West 94 paper. And here's the formula for the best M you should use, minimize mean square error of omega hat, right? And you can see it, well, it increases with t, because as t gets larger, you get more and more precise estimates of the autocovariances, so you can afford to use more of them, right? And it depends on the AR coefficient, because as the AR coefficient goes up, the spectrum becomes more curved and you want to use fewer of the U's. Okay? So, here's the little formula. If t is equal to, 400, if you've got white noise, right, set m equal to 0, right, use everything, right? That just says lambda 0 is lambda 0, right? Just go with it, right? If you got an AR coefficient of 0.25, you should use 5. There's a good undergraduate textbook that suggests this, and I think that probably isn't the best advice. But anyway, be that as it may. And you can see here, of course, as this becomes more and more curved, more and more persistent, right? You want to use more and more lags. But even here, the number of lags isn't really big. It's only 12 for 400, right? And that's because this is a minimizing mean square error. You really care a lot about variance in a mean square error kind of thing. Okay, so we'll come back to that. Okay, so now I want to say, in doing these kinds of calculations, how important is it that you get M right? That you choose a good M? What if you mess up on M? And how important is it that you use kind of the best kernel, right? These are the Newey West kernels, but again, you could imagine in these k-weights, you can imagine other weighting schemes, like flat and comes down, right? That's non-negative. Inverse Fourier transform that would give you the big K's, right? So you could just do, you could just start living down here, right, in the periodogram world, right? And then it's kind of then it's just kernel regression, right? Then it's just kernel regression, right? So you could just so there are lots of things you could do down here. Okay, so both of these things have been addressed. So here's a picture from Don's paper, and this shows the lag window, the capital K's, right, for some different kernel choices. So here's truncated. Keep the first, forget about what forget about the bottom here. Just think about this as going from 0 to 25 or something with lags. So this is the truncated guy. It says keep the first guys and then set everything else to 0, right? Here's the Bartlett kernel, right? So that's Newey West. It's a line, right? And then here's some other things you might, things that have been suggested. Here's the quadratic spectral kernel, right? Which turns out, if you read Don's paper, turns out to be the optimal kernel to use to minimize mean square error. Okay? Here is Tukey-Henning. Here is Parson. Okay? Now don't stare too hard at this, right? I guess the only thing that I learned from this is that this guy right here looks a lot different than these guys. These guys say, right? And this guy says something different, right? So practically, right, all of these guys, for the kinds of data that I look at, it doesn't matter. It matters if I write down some, it doesn't matter. Okay? Yeah, David.
Yeah, if you did the parametric kernel, what would it look like?
It's going to depend on, obviously, the values but for a particular AR, I don't know that. It's going to be complicated. It's different because, right, it's not really weighting, right, let's go back here to what this guy is, right? So what this thing says is I'm going to take a weighted average of these autocovariances, right, where these autocovariances are simple method of moments estimators of those, right? In a parametric thing, what I do is I compute the parameters. Now, they're going to be by least squares or maximum likelihood or something. They're going to be a function of some sufficient statistics, which are going to look like these guys, just a couple of them, right? And then I'm going to apply different formulas. So writing it like this would be very hard, right? Okay, so here my bottom line is I think that kernel choice, again, for the kinds of things that I would look at, I'm just not worried about it. So push a Newey West button just doesn't bother me at all. Okay, so, and the Monte Carlo work that I've seen kind of supports that. I'll show you a little bit. Okay, now, so that's good news, right? That says, don't worry, don't have to look up what these quadratic spectral weights are. Or should I be using Tukey-Henning or Tukey-Hamming? And one has an N and one has an M, and one of them's a guy and one of them's a something, I don't know, a carpenter's tool or something, I don't know. But you don't have to do any of that stuff, right? This Newey West thing seems to be okay, right? Okay. Now, what seems to be, okay, does kernel choice matters? Yes, in the sense that you want positive semi-definite things. You want things to have that shape, okay? Does lag length matter, right? So does M matter? How many lags you put in? That matters a lot, Okay, so that's like that's where the action is here. Okay, so just to show you that, right, there have been bunches of Monte Carlos done in the literature. Okay, and you should read that literature to sort of look at sort of the fine details. I think many of the basic lessons from some pretty complicated designs you can see in a Monte Carlo designs can be seen in something that's really pretty simple. So let's just take, you're interested in estimating a mean. That's it, right? So we're back to our regression that just has a constant term in it. You've got an error term which follows in AR1, so that's going to be W here, right? Because you're just estimating a mean, right? Remember, W is X times regression error, right? The X here is 1. So that follows in AR1. You got 250 observations. So you're trying to estimate a mean with 250 observations. And then what are you going to do? You're going to construct a 90% confidence interval, right? Or equivalently, you're going to do a two-sided 10% test, right? You're going to reject the null that a certain value of beta, right, lies in the confidence interval if the t statistic is bigger than 1.64, right? That's your rule, right? 1.6. I'm sorry. Or you're going to, not include that in the confidence interval if it's outside the beta hat plus or minus 1.64 times square root of omega hat, right? That's your standard error, right? So let's do this. Let's construct or estimate this standard error using a variety of techniques, right? A variety of things. And then let's ask, if you did that, if you use that rule, right, would you reject 10% of the time, which you should, right, if this was exactly right, or more than 10% of the time? Are you over-rejecting? Is your confidence interval too short? Right, it should be longer. Are you under-rejecting? Is the confidence interval too big, too conservative? Okay, so this is what I'm going to do. I'm going to use Newey West, okay, and I'm going to use Newey West where I stick in what Don says I should stick in as the lag length. Okay. Again, Don's problem was finding the minimum mean square error estimate of omega, not controlling size, right? That was not the problem he solved. Okay? So I'm going to go back and use this formula. I know what phi is, right? So I'm just going to stick in that phi into this formula and figure out what m should be. Okay. Now, of course, in practice, you don't know phi. Right? So what would you do? Well, in a situation like this, you might estimate an AR on the residuals, get phi hat, right? Stick phi hat into this thing and figure out what you would estimate the optimal m to be, right? So that would be some plug-in estimator of m star, right? Well, then you might say, well, heavens to Betsy, if I estimated an AR1 model, why don't I just use the parametric estimator from the AR1? Right? I mean, I just estimated an AR1. It's an AR1. You can, right? You just do that, right? So if I took that parametric estimator and stuck in the true value of phi, of course, I'd get the right answer. But now I'm going to stick in phi hat. Okay. Well, then you could be even more sophisticated, right? So you could say, well, maybe it's not an AR1. Okay, so this is what I'm going to do, right? The most sophisticated thing to do is to say, what I'm going to do is I'm going to estimate an AR1. And then I'm going to take that estimated AR coefficient and I'm going to filter the data so that I kind of end up with the epsilons. Okay? Now, the epsilons are kind of like white noise, right? So they have kind of a flat spectrum, right? So I'm going to do Newey West kinds of stuff on this filtered series, kind of like these epsilons, right? And that's kind of nice because I've gotten rid of a lot of the bias, right? So I'll estimate the spectrum from that, and then I'll use my little filtering formula, right, to say, well, what's the spectrum for the original W's? In the jargon, I'll recolor. So the first step is called pre-whitening, making something look like white noise, right? And then at the end, you recolor, right? And you use the little filtering formulas that we talked about in day one. Okay? So those are the things I'm going to do here. This is stick it in using the true value of phi. So this isn't feasible. Here I'm going to stick in 2 times the true value, 2 times m star, just for reasons that'll be clear in a minute. This sticks in m star hat, the plug-in estimator. This says, oh, heck, I'm just going to estimate if I estimate an AR1 anyway, I'm just going to use it. So this is the parametric estimator. And this is this sophisticated estimator where I estimate the AR1, I pre-whiten, that's what PW is. I pre-whiten, I then use Newey West using this optimal M, I then recolor. Okay. Now, okay. So, well, what do you see? Well, if there's not very much serial correlation, all of these things work fine. This says, well, the optimal m star says include everything, right? Everything, it better work, right? It better work, and it does. Isn't that nice? And 2 times 0 is apparently 0, right? So that works as well. White noise, you tend to estimate phi to be really small, right? So m star hat turns out to be 0 a lot, right? So that works pretty well. This AR thing where you estimated an AR coefficient which is 0, you don't always get 0, so you mess up a little bit, right? But in the scheme of messing up, I can live with that. I don't know. Right? It's not rocket science, right? A 10% error. Anyway, if you're shooting at the moon, the difference between that and that might be a big deal, but not in what we're doing. If you're shooting, well, anyway, because we shoot like this far ahead, right? Okay. So, well, what do you see here? You see, as this guy gets more serially correlated, well, what do you see? You see that this size distortion gets bigger and bigger and bigger, right? So by the time phi is, let's say 0.95, there's lots of serial correlation in this, right? Well, the spectrum really has a lot of curvature in it, right? This estimator, it's a minimum mean square error estimator, but it's still got a big bias, right? And the big bias leads to over-rejection, leads to under-rejection of the null. You reject, you have a size of 46%, you reject the null far too often. Confidence intervals are too short. Now, you do a little bit better, not surprisingly, if you put in more lags. It's still, life isn't great, but the parametric estimator, well, it works pretty well down to, 0.8, 0.9, right? That's not a major sin, right? It starts having a problem here. Why? Well, you estimate an AR coefficient when the true AR coefficient is 0.95. You get downward bias, right? So you're sticking in a downward bias thing. This, as it turns out, always works kind of like this, right? Why is that? Well, you take the data, you pre-whiten it, right? And then you give it to some Newey West kind of thing, and you say, oh, tell me how many lags I should put in. And it says, this looks like white noise to me, right? And if it looks like white noise, it says stick in 0, right? So these 2 columns are, if you look at lots of these Monte Carlo things, these columns are often very similar, right? Because the pre-whitening, right, does nearly everything. Okay, so the lesson here is, these things tend to put in too few lags. And, yeah.
The AR, it's an AR.
Yeah, so exactly. So this is cheating. This is cheating because so there are more complicated designs where you really want to start out with something complicated, and I approximated by this AR1, so that's not going to be right, and blah, 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 and blah, 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 right? Absolutely, right? So this isn't the definitive Monte Carlo, on this, okay?
If you did like AIC or something with this, would it, but with the same model, would it still pretty much pick the AR one most of the time and do that as well?
I don't know the answer. My reading of the Monte Carlo literature, and you may know more about this, Haley, people may know more about this than I do, is that you tend to get this kind of thing. But okay. This paper has some. I thought it had more. I reread it last night. They've got a couple of papers, most of which are unpublished. This is the only published one, which is in some obscure book, but it's on Wouter's website, so you can download it and look at it. Maybe some of their other papers had more. I remember seeing many more Monte Carlos in their work, which I thought had this flavor, right? Has this sort of basic flavor. Okay, now, there's a paper. There's a nice paper in Econometrica, like this year, and another follow-up paper by Sun and Phillips that kind of explains why this is going on. And, the argument, in a nutshell, is pretty, well, I think you can see where the argument comes from with just a couple of lines here, right? So they're thinking about, how should you choose bandwidths? How should you choose M, right? Not to minimize mean square error of your estimated variance, but rather to think about what the size distortion would be in a test, right? So what they do is say, well, here's the cheap version, right? Here's the cheap version of this long, beautiful technical paper, right? So don't ever tell them I did this, and this is just, let's think of this as a heuristic, right? That you're allowed to say that, right? So a heuristic is this, right? Which means it's chock full of errors, but hopefully has some insight in it, okay? So Z is normal 0 sigma squared. Easiest model in the world, right? You got a normal, right? And you don't know sigma squared, so you stick in sigma hat squared. Okay, that's our problem, right? Let's figure out, so this would be like, if I put in the true sigma squared here, this would be like a, standard normal squares. This would be a chi-squared, right? So I want to do chi-squared like inference, but I'm putting in sigma hat, right? So what's the probability that my, if you will, Wald statistic is less than C? Well, that's just rewriting. That's the expected value of this indicator function. I'll just call it the expected value of G, right? And now let's do a little Taylor series we'll do a little expansion. These guys are going to use an Edgeworth expansion, right? I'll just mumble. I'll say Taylor series or something, right? And so around, sigma hat squared is equal to the true sigma squared, right? And then what do you get? Well, if I just sort of said I can do this, which, I can't, but if I just said I could, right, well, what would I get? Well, I would get, this guy evaluated at sigma squared. That's a chi-squared, right? And then I'd get the first term in my expansion, right, which would be the expected value of sigma hat squared minus sigma squared times the first derivative plus, 1/2 the expected value of, this guy squared, right, times the second derivative, right? Well, what's mean square error do? Mean square error says, I'm really concerned about this, right? But, right, what do I want to do here, right? It's not only this that I should be worried about. I should be worried about this term as well. I want to make this small. I want to make both of these guys small because I'm approximating this guy with this guy. So I'm worried about both of these guys, right? So I really do care about this bias term. This bias term is important, right? So I got to think about the relative magnitude of this G prime and G double prime, right? They both turn out to be important, as it turns out if you crank through what's going on here. So this bias term turns out to be important. So bias is more important for these kinds of calculations than would be suggested by just doing mean square error stuff. So this says you want M to be bigger than would be suggested by sort of standard mean square error formula. So you see, right, making M bigger helps. It doesn't help a lot, but it helps. Okay, now here's, there's some really great, interesting work in a series of papers I'm going to call them KVB papers, in which one interpretation of what these folks do, is just to say, if M should be big, let's just make it big, right? Let's just do it, man, right? So, how big can M be? How big can you make it? Well, set it equal to the sample size. Just include everything, right? Holy moly, right? So, boom, just do it. Now it's going to be important for some calculation I'm going to do in a minute, that now I want to be clear I'm putting W hat in here and not W. I want to be clear about that because the first time I wrote these slides, I put in W and I didn't get the right answer and I kept getting stuck. So it's because you really need a W hat. Now, W hat's the right thing to use because for everything I've said before, W hat doesn't matter. For this, it does. Okay. Well, then, what these guys, what's shown, right, is this Bartlett thing with T is equal to M. You can do some algebra. And as it turns out, you can write this guy like this. Okay, now, why do you care about that? Well, it's easy to figure out, not easy, but one can figure out in a pretty straightforward way what the limiting properties of this thing are, right? Using these empirical process methods that we talked about in day 2, right? This is just like a Wiener process. And yeah, I got W hats instead of W's, right? Added up squared. This is like integration, right? And there's this magic 2 here, which again I left out of my first slides, and which was a major sin. Okay? But blah, 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 blah. I'm going to go to the next page now. Blah, 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 blah. Here we go. So this says, think of this Newey West guy with T equals M. Okay? And how does that guy behave? Well, how would a consistent estimator behave? A consistent estimator, I'd write down there, omega hat converges to omega. Right? Now what do I write? Omega hat converges to omega times a random variable. Okay. So this estimator is not going to be consistent. Okay? Now, let's go back. Do I have it? This just uses M. This is the Bartlett kernel with M is equal to 50. These guys are using M is equal to 250, right? What's the little k weight's going to look like for M is equal to 250? Well, they're going to be putting a lot of weight on just the first couple periodogram ordinance, right? And so they've got a very small sample that they're using, right, to estimate omega, right? So of course it's not going to be consistent, right? It's just based on a few observations. Now, it's going to be really robust, right? Because it's not using any of this information down here, right? Which is good information if the spectrum's really flat, but is really killer bad information, biased information, if the spectrum is really curved, right? So this is going to be kind of a really robust estimator. It's only using the information that they're kind of sure of, right? That's very close to the origin, right? And the cost of that is that you don't get consistency, right? You get some sampling uncertainty that is always going to be there in omega hat, just as it is in the t statistic in the normal case where we're constructing a confidence interval and we have a sample of size 6, right? And s squared, we think about s squared in the denominator. So instead of using 1.64 is our critical value, as we would in a Z thing for a 90% or 10% test, right? We use the T thing with, 6 degrees of freedom or something, right? Okay, so that's what this is. And, sure enough, you can, look at, well, here's the critical values here. Here's the critical values for their t-test like thing, right? So instead of using, 95%, a 5% test, right, you'd use 1.96, right, if this was a consistent estimator. If it was normal, these guys are going to use 3.7. Where's the 3.7 come from? You're using s squared in the denominator instead of sigma squared, right? And it's the right way to think about this problem if you want to be really robust, right, to curvature, right, of the spectrum around 0. These are the T critical values. You can look at the F critical values there in the original KVP paper, but the way I've written it here, you have to take those and divide them by 2. That's another mistake I made at one point in my life. Okay, it's because in the original KVP paper, they proposed, I can't do it, they proposed that thing, and then in a later paper, they said it's the same as this thing, but with a 2 in front of it. Right? So, okay. So I'm almost out of, here's some like power stuff for their method. In the normal stat 101, in the normal case, knowing sigma squared is not better than knowing sigma squared. And so if you knew sigma squared, you should use sigma squared instead of s squared. And by using s squared, it costs you a little bit, right? And that's what this says. This is what it costs to use this sort of robust estimator in terms of power. Okay. More Monte Carlos. I'm not going to talk about that. Here's some advantages and disadvantages. I'm going to let you read these. These are pretty straightforward. What I talked about already. I've got 2 minutes left, so I want to go through. I just want to talk about one more thing, which are some cousins of this. This work, this sort of KVB work, right, is related and inspired, lots of other work that has been done where people are constructing covariance matrix, estimated covariance matrices, which turn out to the authors would argue, arguably reflect the underlying uncertainty in the estimate of the variance. That is, that recognize that s squared isn't equal to sigma squared and try and incorporate that in the inference. Okay, so and all papers that do that now say, well, this is sort of like, this is analogous to KVB. Okay, so one paper is by my colleague Ulrich Müller, who really it's a great paper, talks about robustness issues. But his point is that he's made in sort of several papers is kind of this. He says, here's the calculation. He says, look, you're trying to estimate a low frequency, long run thing, spectrum at frequency 0 or something, right? So that's long run variability in the data, right? How much information do you have about the long run, right? Well, a little calculation, right, that might help one think about that is, well, let's define long run. We have to be kind of specific about that. Let's define long run as, variability in the data with a period which is greater than, I don't know, P. Choose P. 6 years. Right? Well, how many periodograms do you have, of course, with frequencies, right, whose periods are bigger than 6 years, right? We'll do the calculation and you get, the usual kind of thing. If I've got 60 years worth of data, right, and I'm looking at variation over 6 years, how many independent sources of information do I have? Well, 60 divided by 6, right, which is 10, right? So you really have 10 observations that you're using to sort of figure out that low frequency variability, and you don't want to sort of look at a bunch of algebra on a page, Woolrich would argue. You wouldn't want to look at a bunch of algebra on a page and say, well, gee, there's Newey West told me this is consistent, so 10 must mean infinity, so I can ignore sampling uncertainty in this thing, right? He would say, no, you want to recognize that you only have 10, right? So include that in your when you're doing inference, right? And one could do that in the KVB way or in other ways that's suggested here. Related to this is, it doesn't look the same, but it's sort of similar, is a paper by Christian Hansen. It's not doing time series analysis as this is. It's a panel data problem. And what Christian talks about is, suppose you're doing clustered standard errors in a panel data situation, and in one dimension, let's say the t dimension, right? You've got a large number of observations on one person over time, so you want to cluster on that, right? But you've got a small number of people. N is small, right? And what he shows is if you use the sort of standard clustered errors coming out of panel data, that you get the same kind of thing. If you do inference, you should account for the fact that you have a small number of individuals, right? And shows that, you get some nice limiting results. You get t statistics being distributed t, right, with degrees of freedom equal to n, or n minus 1, I think. And F statistics have a similar kind of distribution, appropriately squared. They're Hotelling t squared things. And there's some other work that I unfortunately don't have time to talk about. So let me go to the bottom line here of this lecture. In these designs or in these worlds where you have moderate serial correlation, moderate memory, AR1s with coefficients up to 0.7 or 0.8, that kind of memory, that kind of curvature in the spectrum, right? My reading of the literature is that these parametric estimators seem to work pretty well. So doing VAR, taking these W's and estimating a VAR model and then computing the implied omega, right, seems to be a pretty good way to work. In many applications, like you're using these for forecasting assessment, right, then you have a theory which says the error should be MA3s or a certain MA process, and then it's very clear what you want to do. You want to go out and estimate the MA process and use that, right? Why do one of these do one of these non-parametric things when you know something's in MA, right? Just do it, right? You need to ask yourself why you're estimating omega, right? If you're estimating it for inference, right, you probably don't care about minimum mean square error estimates. You probably care about size, and then you want to include more lags, or you want to do a KVP or one of these other robust estimators. If you're using it for optimal weighting in GMM, that's a different problem, and then maybe that's closer to the mean square error thing. You don't want a lot of uncertainty in that weighting matrix. Okay. So that's it. So that's the end of this. Let's take, if we can, let's take about a 25-minute break and then come back for my final lecture.